Today we're going to talk about the constant volume depletion test, which is as the name implies, a test to study the depletion characteristic of gas and oil properties using a constant volume procedure, which we'll talk about. This is discussed in some great detail in Chapter 6. And in the eNote directory called PVT Papers, there's a paper there that you probably should have a look at. It's called Evaluating Constant Volume Depletion Data. And it is not only recommended for, I don't think there's a lot about the experiment that's covered in the paper that's not included in Chapter 6, but this paper also gives an introduction to the next topic, which is modified black oil PVT. Which is, again, the topic of Chapter 7. So it's kind of a good introduction to that as well. So I strongly recommend that you read that paper, and I may put it on the required reading for the course. This depletion test is, as I mentioned earlier, it's conducted on primarily gas condensates. And gas condensates, as you hopefully now realize, are mixtures where you measure a dew point at reservoir temperature in the laboratory. So the saturation pressure is a dew point. And so it's typically the standard procedure for measuring depletion characteristics of a gas condensate. But it also may be used for what I'll put high GOR. I think we talked about greater than like 4,000 or greater than around 400-ish standard cubic meters per standard cubic meter oils. Sometimes these are called near critical or highly volatile oils. Okay, so that would be yet another set of new terms for you: near critical or highly volatile oils. Okay, so this is the test that we'll go through today. Now, the test is conducted at a reservoir temperature, which is remaining constant, and you will be using, or you won't be using it, but the laboratory will be using a PVT cell, which has a visual window. In other words, you can observe the meniscus of gas and liquid. So we'll be using what's called a visual PVT cell. There are different kinds. I'm not going to go into the details of that. I'll just mention that you have the old traditional Ruska 3-windowed cell. We probably could go down in one of the cellar rooms and find an old example of that, the Ruska 3-windowed cell. And then today they have, this was actually intended to be used with mercury as the material to pressurize and change the volume of the cell. So you add and remove mercury, which hangs down at the bottom of the cell because of its high density. And then you've got some mercury-free type cells. There's probably some up on the 4th and 5th floor at Syntec Petroleum. And there's a number of different methods, but they basically use pistons to change the volume. They have maybe piston on the top and the bottom. I don't know all the different types, but one version of that would be a cell that maybe try to do this without being too bad. So let's say that the looks like something like this. A little bit. Okay, something down like that. And then you've got a piston system that you can move the pistons, up and down the bottom and the top. And what you're trying to do is you're trying to do that to change the volume, but you're also trying to do that to get the interface of what would be the oil and gas interface that you see it. So there's kind of there's basically your eye is here. Okay, so there's a visual inspection where this becomes small, the cell. So there's maybe it's a glass here, so that you can see through it. So you can move the gas and oil up and down, change the volumes, and you can basically inspect it like that. There are other types of cells, but something like that. The point is that you actually, with these cells, all of them, you have not only a measure of the total cell volume, but you also have the oil and the gas volumes each. Okay. Let's see. And then another important part of this laboratory test is that you are very interested in getting accurate compositions of the gas phase during the test. Okay, so you're interested in doing gas removals, which will show kind of how it's done. But one of the main data, if not the main data, you're trying to get accurately is the molar composition. Which I'll just write YCVD I, component I. And in particular, what you want to get accurate, you want to get all the components accurate, but you particularly want to get the amount of those components that form liquid at the surface. So certainly C4, 5, 6, 7, and heavier. So the certainly most important here are what I'll call the stock tank oil forming components. Those components that will be found mostly in the stock tank oil. So I'll just basically say something like certainly C5 and heavier components, probably even, all of the components, but you really want to get that amount correct. So I'll just hit. Okay. And because those compositions are important, and particularly the heavy amounts, when you remove material from this cell, basically when you take out, when you remove here, that has to be done in a way that you don't lose any of those heavier molecules as you're taking them out and moving them to some sample container. Okay? And if you have any cooling that goes on between the exit point where you're taking something out and where you actually collect the sample, okay, if the high pressure wire, metal lines that you're removing it in, if they are at a lower temperature than what's in the cell, then you'll get condensation. And what condenses first? These components that you're mostly interested in. So there's special equipment and procedures to guarantee that what you remove remains as what you removed, and that you don't lose this little drop of liquid that might be a large amount of the material that's forming the stock tank oil. Okay, and what might be 1 cc loss here could represent tens of thousands of barrels per day incorrect estimate of what that gas will actually deliver in the way of condensate. Okay, so you have to be very careful. So there's some special considerations in the equipment. So we use a visual cell. We have some special procedures to make sure that what we remove in the way of gas is kept intact, and the entire experiment is conducted at reservoir temperature. So, all right, any questions? So we haven't really talked about how the procedure is done, but we'll go through that now. So we start the experiment. This is all at reservoir temperature. We start the experiment. The first pressure is equal to the saturation pressure. Could be a gas, could be an oil. So it's at the saturation pressure. In this volume here, we will just write saturated volume. It's a very important volume. And then we'll lower the pressure. And what will happen is that the total cell volume will increase, of course. And I'm going to sketch this example as if we're starting with a gas, because that's the most common. So we're going to start with this gas, which I'll just indicate by the red here. Okay? And of course, at the dew point, there's some little drop of liquid that we don't see. We don't see it, but it's supposed to be there. So then we go to here, and now, since we're at lower pressure, we condense out through retrograde condensation some liquid, and that forms at the bottom of the cell. And the rest of this is, of course, gas. It's a different gas. It's a gas that is what we call leaner. It's a leaner gas because lean and rich is referring to money, okay, and or C5 plus content, which is the same as money, because you remember the 22 factor of 22, more valuable sold as an oil than sold as a gas. So those components that you know, if we took this first gas to the surface, we might get 200 barrels of oil. But if we take this second gas to the surface, we're going to get 160 barrels per cubic meter of what we take out. Okay, we're going to get less condensate. Why? Because that 40 barrels we lost is now a liquid in the reservoir. Okay, so the components that form the liquid in the reservoir, they're depleting those components from the gas. Okay, so this gas is becoming leaner than the original gas. Okay, I'm going to just sketch this like this. So at this point, we've got a total volume that's bigger than the initial volume. And here the experimental procedure is going to be such that we try to mimic what goes on in the reservoir by always maintaining a constant hydrocarbon pore volume. Okay? That's kind of the concept. And to return this new cell volume back to the original saturated cell volume, we can take away all of the oil, part of the gas. We can take away all of the gas. Those are the two options. And what's done is that we basically go in and we take away this gas here. Okay, so that's removed. And then we're left with, at the same pressure and same temperature, P2, we're left with this same oil. Nothing changes. Like we talked about yesterday, nothing changes if we take away part of the phases. Okay, this gas is exactly the same gas that we had. It's like, you know, putting the lady in the, you know, the magician. I like the, you know, you cut her in half. Well, it's still the same lady. It's just you kind of lost half of her. And at the end of the trick, put them back together, and it's the same lady. Okay, so the deal is that it doesn't really matter that we've got this gas here removed. This gas is exactly the same as this gas and that gas. They're all the same. And this oil is the same as this oil here in amount and composition and everything else. So the equilibrium doesn't change because you take away some of the phase. Okay. So we're back to the same VS volume. We've removed this amount of gas, and what we actually measure in the laboratory is how many moles of gas were removed. We know the volume of that gas that was removed at pressure and temperature, at the pressure. Of course, we can convert the moles with our 23.68 number to a equivalent surface gas volume, standard cubic feet, standard cubic meters, right? We measure this oil volume here. We always measure the composition. I told you that was one of the important things here. In the differential liberation test, it was an optional measurement. Here, it's not optional. You always measure the compositions of the gas removed. And it's done, hopefully, in a very careful way. So these are all the measurements that are made. This is basically one stage. This is stage 2 in the experiment. Yesterday I forgot to tell you typically how many stages of differential liberation depletion do we have. I was going to tell you and I forgot and nobody asked. It's 623. No, I'm just kidding. I mean, since I didn't tell you and nobody asked you, everybody went home. Some with 623, some with 6, some with I don't care, you know, I mean. So, but basically, the differential liberation test has typically somewhere between 6 and 10 stages. Usually, yeah, something like that. In the constant volume depletion test, because it's a little more expensive test, you're measuring the composition each time. Typically 6 stages on average. 6 of these stages. The last one being standard pressure. Okay. So I'll say, you know, usually of 6, you might in some cases have 8. Okay. And then just on the same line here, I'm going to bring it to Pn minus 1. And what I'm going to do here is that I'm going to put it at a volume that looks like this. And now we've basically reached this Vmax of the cell. Again, because we're at low pressures, this is typically, anywhere from 250 maybe to 750 psi. Probably not 250, probably 500 to psi. 30, 50 bar. And we reach the max volume of the cell. And when we reach that, this is actually a little bit over here. And now we're trying to get down to 1 atmosphere. Okay, we're trying to get there, but we can't get there by just expanding the volume. So what you have to do again is that you have to bleed off the gas to reduce the pressure down to 1 atmosphere. And that, as we talked about yesterday, is not really an equilibrium process. It's approximately that, but you basically bleed it down until you get 1 atmosphere. Okay. And then in a sense you kind of reach this condition that you're back to the volume. It doesn't really happen that way, but we'll just say that all of what was bled here, all of this is removed. Okay, so that would be the last amount of gas in stage N. Okay. And the oil volume might look something like this. It's usually maybe not at a maximum here, but it's maybe close to a maximum. Probably the maximum oil volume was somewhere in between, 2,000, 3,000, 1,000 psi. So we end up with same kind of measurements. We get the moles of gas removed each stage, the actual volume. In the last stage, of course, the volume would be at 1 atmosphere. So these two numbers would be the same at the last stage, and the composition of the final gas. So that's the experiment. We make one measurement of the oil, that's its volume. And we make multiple measurements of the gas, the number of moles removed, the volume removed, and its composition. That's pretty much it. Okay. Now, what's interesting about this experiment, or what's important about this experiment, is that for gas condensates, which is 98% of the experiments conducted are on gas condensates. In gas condensate reservoirs, the oil that comes out of the gas stays in the reservoir. Okay? Okay? In general, this is a blanket statement. This is like, for practical purposes, even the richest gas condensate, the one that will release the most condensate down in the reservoir, 30-40% of the volume. Okay? For practical purposes, that condensate comes out of solution, it sticks to the rock. It sticks to the rock. It's not coming our way unless we spend a lot of money to try to get it to the wells. It's not just going to flow into the wells together with the gas. Okay? And the reason for that is that in reality, in gas condensate reservoirs, and I'm just going to put all, the mobility of oil in the bulk of the reservoir. There will be an exception very near the well. I'm going to ignore that because it's an exception that is a very small part of the volume of the entire reservoir. So this average mobility in the bulk of the reservoir, and I'm going to say 95% of the volume of the reservoir. That's pretty much everything. This is essentially zero. And it's certainly, even if it's not zero, it's much less than the gas mobility in the reservoir. Okay? So the gas mobility, its viscosity is lower, its permeability is higher, so that effectively in a gas condensate reservoir, the only thing flowing into the well bore is a gas phase. We still make a lot of money off of produced condensate in gas condensate reservoirs. How can you do that? It drops out in the reservoir, it stays in the reservoir. That's what Curtis says, okay? So how are we making all this money at the surface from condensate? Even if we don't. Even if we drop the pressure below the dew point. Let me try to put it to you this way. The air, when you go outside in the morning, like today, half of the windows had dew, water on the windows. The other half of the car was iced. I hate the winter. Yeah. So basically this water condense on the car, where did it come from? The air. Okay? Because the temperature on the window was colder than the air, I guess. Now, the question is this. Since I see condensate on the window of the car, do I go outside and I think, oh, wonderful, there's 0% humidity in the air. The air has no more water in solution. You know what humidity is? Fuktigkeit. Oh, there's no Fuktigkeit in the air. Is that the first thing I think because I see the condensate on my window? No. It's the same deal here. Just because some of the condensate dropped out and stays in the reservoir doesn't mean that there's still condensate in solution in the gas here. That gas comes to the surface, it's still got 160 barrels of oil that stayed dissolved in the gas until it came into the well and went up. Now, when we produced this gas in the early days, we were making 200 barrels and life was better. Okay? But 160 barrels at $107.90 as it is today is still not a bad thing. So the point is that the gas is becoming leaner, okay, but it still contains a significant amount of condensate in solution. And the interesting thing about this experiment, given that, well, you may not believe it, you can prove it to yourself. I could prove it to you, but I won't. But this is the fact. Okay? So the interesting thing about this, in this constant volume depletion experiment, what is the fundamental assumption? The fundamental assumption is that this oil here has what mobility? Zero. It's not going anywhere. That's a pretty damn good approximation. We're also maintaining this constant volume. kind of like the hydrocarbon pore volume, ignoring the compressibility of the rock and the water. So it is actually mimicking the reservoir depletion process almost exactly, or certainly very closely. And that means that the information we're obtaining, the most important information is how many barrels do I keep producing? Okay? 160 or 200 or 110 or 60. Okay? That's the most important information because that's where we're making most of our money. This experiment, through the gas composition, and in particular the composition of these heavier components, whatever we decide to call our stock tank oil components, basically knowing how many moles we produce, but in particular, for every mole, how many barrels of condensate do I get out? This experiment is telling me directly. That's why it's a very important experiment. It's why the compositions are very important. And that means that it's very important to make sure, are my compositions accurate or not? And the paper that's referenced for you to read is talking about doing things to check the quality of the compositions that are measured in the experiment. Okay? So that's there's some quality control checks for how accurate are these compositions, what we call quality control checks. Okay.
So can we then use the measurements and all the parameters we get out of this experiment, use that directly in our calculations?
You can. You can use them directly in the calculations. Now, yes, you can use them in many types of calculations. Now, most reservoir simulators, many simulators, won't allow you to input directly. You'll have to transform the data into the information the way the programs want it. But yes, you could use directly and can use directly these data. So, which is a good observation. So now let's just look at what's actually reported by the lab. Okay, the first thing is our compositions. I'm going to write it this way. As a function of the pressure. Okay? For each stage. The moles produced divided by the moles that we start with initially at the saturation condition. Okay? So it's like a percentage, it's like a recovery of total moles from what you start with at the saturation pressure. Now sometimes they'll express it in moles per mole. Sometimes they express it as standard cubic feet per standard cubic feet, or million standard cubic feet per minute. So sometimes they report it as I won't use initial here, I'll use at the saturation. Okay, so this might be given in million standard cubic feet per million standard cubic feet, some kind of strange unit, or as a percentage. It's the same thing, okay? Because these gas volumes that are being talked about here are so-called wet gas volumes. They're surface standard condition volumes, ignoring the fact that that gas will actually produce condensate. Okay, they're wet gas. These are fictitious, what we call wet gas volumes. It ignores the condensate part of production. So I'll go ahead and add the term W here. Wet gas volumes. So these are wet gas volumes. This ignores stock tank oil produced at the surface. So it's really, that's kind of stupid when you get so much more money from it. But for the laboratory, that kind of volume is the same as a mole. It's just the 23.68 conversion between the two. And they used to make these reports for people in Oklahoma, like me, and you don't grow up learning about moles in school, or you forget about it as an engineer, but standard cubic feet, you know what it is. So it's kind of to make things more convenient for engineers, some engineers. In reality, this is what's being measured, and often it is reported that way as a percentage. The third thing they report is the Z factor. That's calculated by the moles produced. Let's see here, I have to get this right. Pressure, the volume that was removed, the moles removed, gas constant, and reservoir temperature. Just like we did in the differential liberation test. So this is calculated. By the way, they may give you an estimate of the molecular weight of the heavier material in that gas. This would be an estimate. It might be from the chromatographic analysis, GC analysis, or just some estimate. It's not really correct to say estimate. I'm going to take this way. It's coming, they don't measure the molecular weight itself of this very small amount of C7 plus. But they either get it from the chromatographic analysis, where I talked about this, you've got this, you do the GC analysis. In order to do that, you have to flash this removed gas down. You get a little droplet of liquid, and they might do a GC analysis of that liquid, and they get this. So this is the flashed oil from the removed gas. There's probably only a little bit of it. This is the GC analysis, and this might be C7. So they kind of estimate, they know the amounts here. Try to make some estimate. Or they might, when they take the gas out, they actually may weigh it in a glass bottle. They have an evacuated gas bottle in which they produce into it what's taken out. It fills the pressure to 0.8 bar. They just weigh it on a scale, so they know the mass of material, they know the volume of the glass bottle, and they know it's 0.8 bar. So they make kind of a, or from the molecular weight of the gas that's removed. But anyway, this is sometimes an added that's usually reported. Is there anything else with the gas that we said was measured? So we've got, this is being used here, this and this to get the Z factor. I think that's it on the gas. They might report the viscosity of the gas, calculated. So this would be sometimes gas viscosity calculated. And then what they'll always report on the oil is the oil volume divided by that saturated volume. Okay? So that's always reported. as a percentage. And that will typically, that's called the liquid dropout curve. So sometimes I think of the dropout curve of the class, how many end up coming to class as they realize they can watch in with a something cold to drink instead of coming here on, particularly when I have 8 o'clock lectures on Monday. The dropout curve from the class is like is falling off. But this liquid dropout curve is what we call this, and it will typically look something like this. Okay, it'll have some kind of a maximum. The last volume will typically be close to the maximum. It won't usually be the maximum. It'll be something like this. And this maximum, what we call the maximum liquid dropout curve value, is often used as a label, as a sticker. Okay, new discovery, gas condensate discovery. The president of the company happens to be coming by, drops by. What's his name? Helge drops by and says, "Hey, Lars, I heard we got a new discovery, no gas condensate discovery." And Helge will say, "What's the maximum liquid dropout value?" Because he maybe studied reservoir engineering. It's kind of a number. Oh, 2%. Oh, that's too bad. Because if it's 2%, it's not very much. He realizes that it's only going to have 20 barrels. It's only going to be selling 20 barrels. Okay? If you say, oh, it's got 35% liquid dropout, maximum 35%, he's going to think, oh, that's good. I'm going to get 280 barrels out of this one. Okay? It's kind of a gauge. So this basically gauges, in a very semi-quantitative way, the richness of the gas condensate. And typically it'll range from 2 for a very lean gas condensate to as much as 40%, maybe plus, for very rich condensates. Okay. I was just joking. Helge Lund wouldn't know about the maximum liquid dropout curve. But, you might ask about how many barrels per million it's got. That's kind of number because it's much closer to value. So, okay. So that's pretty much this experiment. So we'll go ahead and take a break, and then we'll look at actual data from such a test.